So hi everyone, thank you for joining this session. My name is Ohad. I'm a big data developer in PayPal Israel, and I'm part of the Global Risk and Data Science group. My group's job is basically to provide solutions to manage the risk at PayPal. We handle fraud risk and credit risk for both the consumer and the merchant. My specific team in the group focuses on building graph-based solutions. We explore the technological, analytical, and algorithmic aspects of these kinds of solutions. In this talk, I would like to tell you about one way in which we build such solutions, and also review a few of the algorithms that we use. So let's start with how graph data looks like at PayPal. So this is an example of the data we have. This is basically the digital footprint of the user activity as we see it in our systems. And our target is to extract as many solutions, as many insights as we can from this graph. And we can go in many directions. So for example, we can group user accounts that share the same assets. Or maybe I will say, we see essentially a bipartite graph from the user account to their assets. And then, as I said, we can group together user accounts that share the same assets. And this group of accounts might represent a person, or a household, or a business. Or we can go in another direction and connect assets that are used by the same users. In this way, we can identify fraud networks, and there are many other applications. So to motivate this talk, I would like to tell you about one such application, which we call IP nets. So in this solution, our goal is to connect together medium-sized and relatively static groups of IPs. And why would we want to do that? So first, we want to boost the signal. So if a user logs into our systems from a certain IP for the first time, we can't say much about that. But if he is already logged in from another IP, from the same IP net, we can easily leverage this information. Another example, you could think about P2P money transfer. So it would be much easier to enable the transfer if both peers use the same IP net. So how did we build this solution? The first step was to create this graph. I don't want to stall too much about this step, but I will tell you that most of the heuristics and logics are in this step. So we had to filter out noise. We had to filter out weak edges that don't help us in these specific solutions. We also had to handle very high degree nodes like big ISPs, like British Telecom ISP, which has hundreds of thousands of users that are essentially background noise for this application. So the second step was, after building the graph, we need to group together the nodes. So first, we tried to run a connected components algorithm. But basically, what we got was just one giant component with all the nodes in it, and we understood that we have a very highly connected graph. So we tried to run strongly connected components. And the results got a little better, but still far from what we were looking for. And then we changed a little bit the approach and tried some community detection algorithms, and the results got much better. And this is what I would like to focus in this talk. So let's take a step back for a minute and talk about the main challenges we had to consider when we built this solution. So first, the data itself. So in PayPal, we have huge amounts of data, and that dictates both the technologies and the algorithms that we can use. So in this example, we had a graph with about 500 million nodes and more than 20 billion edges. But in other solutions, we have much bigger graphs, and also in this solution, we expect to grow much bigger. Second, no data is perfect. But here, as I mentioned before, we don't handle only noise or missing links in the data. We also handle good data that just don't help us in the specific insight that we're looking for. Next, the graph itself. So this is actually a huge point and maybe a subject by itself. And it talks about how do we take all these different kind of nodes and different kind of edges and their respective properties, and encode all this information essentially to the graph topology and the edge weights. We currently are doing this heuristically, in essence. So this is this point. Next, the community detection algorithms themselves. So because the amounts of data we have, it was obvious to us that we have to use distributed algorithms. However, while single process algorithms, we have a wide variety of algorithms to choose from. Only a few of them could be implemented in a distributed manner, and even less will be implemented in any technology that you'll choose. So for example, we use graphics, which is Spark's graph algorithm package, and it comes with only a handful of algorithms, and actually not even one community detection algorithm at all. So each algorithm we wanted to use, we had to either find in the open source and migrate, or implement ourselves from scratch. Next, after we have a few algorithms to choose from, they are essentially unsupervised algorithms on one hand, and we have no ground truth information on the underlying communities that we're looking for. But we still have to choose between them. So I'll talk about ways to measure the different results and to pick the best algorithm. So in the rest of this talk, we'll review a few of the community detection algorithms that we used, and then I'll tell you how we chose between them. So we'll talk about two families of approaches for community detection algorithms, and we'll see one example algorithm in each family. And we'll start with the objective measurement optimization family. So here, as I said, in the clustering world, most of the algorithms are unsupervised. But you still want to evaluate your results somehow. So there are several popular objective measures to evaluate your results. And this family talks about choose one such measure and try to change your current clustering results in a way that will increase this specific measure. So let's see an example. And don't worry about the function. We'll walk through it together. So the modularity function, it's an example of an objective measurement function. And where you have clustering results, like this one, for example, on this specific graph, we can just plug in the numbers and calculate the score. So this delta function over here tells us that we just need to iterate over each cluster on its own, and then we get a positive contribution from all the edges inside the cluster. So A is the adjacency matrix, and Aij is the link between node I and j. And we get a negative contribution from all the degrees of the nodes inside the cluster. So di is the degree of node I. And m is just the normalization factor. It's the total sum of all the weights. So this function is meant to compare, or is designed to compare how dense are the edges inside the clusters compared to the chance that they will get connected randomly, just to get a hang of it. So now that we have calculated this measure, let's say we run another algorithm as another clustering for this specific graph, we can again calculate this modularity score and choose the clustering that yielded the higher score. And now this function has a very nice property, which is it is essentially an independent sum of each node and its own contribution to the modularity score. And we use it first to easily calculate in parallel the modularity score So we can do it on each node alone and then just aggregate the results. And second, and more important to us, because each node knows not only its current contribution, its node knows also what would happen if he changed his current cluster to a nearby cluster. So let's see it again slowly with an illustration. So we start far from the left with each node in its own cluster. Then each node looks at its neighboring clusters and moves himself or transfers himself to the cluster that will yield its own maximum contribution to the modularity score. So we do it over and over again on each of the nodes until no node wants to change its own cluster. And because each node in each step in the process is doing what's best for him, we call this process a greedy process. So this is the greedy way to optimize the modularity score, the modularity function. Now, we can even take another step. And after converging in the first stage, from moving from left to the middle, we can now compress each cluster to a supernode, and thus form a super graph, and feedback this super graph to the greedy process again. So this two-stage process is called the Louvain algorithm. It's a very popular algorithm in the community detection world. It's very fast, it's very scalable, it's easily distributed. It gives us also a natural hierarchy of clusters for each of the nodes. Its cons are that because it's based on a greedy process, we are not guaranteed to converge to the global optimum. And also it has a little problem known as the resolution problem, which says because we are trying to optimize the global measure, it's not very sensitive to small local changes. So this is the Louvain algorithm. Now, when we wanted to use this algorithm, we found an open source implementation. It was quite good implementation, actually. So we just took it over Spark. We migrated it to work with our current version of Spark, which is Spark 2.0. And we had to change a little bit the function that you saw, because this function is meant for undirected graph, and we use the directed graph. So this is about the Louvain. Next, let's review another family of algorithms. So this is the random walk family. The intuition behind this family of algorithms is if you start a random walk from a certain node, then you are more likely to end this walk on this node's cluster rather than to move to another cluster. And let's see how it is implemented at MCL. So MCL is short for Markov clustering. It's an iterative process, which each iteration is composed of two steps. The first step is called expansion. In this step, so you actually start a random walk from all of the node, and you do, for example, a two-step random walk. So you start from a node, you choose the outgoing edge according to a weight, according to a probability that is proportional to the edge weights. And then you do a two-step random walk from all the nodes, the all possible two-step random walks. This step, so thus you form a new graph based on the two steps random walk, and this is why it's called expansion. Now this step is implemented essentially by representing the graph as its adjacency matrix, and then multiplying the adjacency matrix by itself. So this is the expansion. Now the second step is called inflation, in which you tweak a little bit all the edge weights, and then you threshold them in order to be left only with fewer edges, but stronger edges. And then you iterate these two processes again and again, until hopefully each node will be connected only to the center of its cluster. So this is the MCL algorithm. Its main complexity comes from the matrix multiplication, the adjacency matrix multiplication. And when we wanted to use this algorithm, we found only an initial draft work in GitHub. Then we reached out to the guy who wrote it. We collaborated with him. We fixed a few bugs. But the main problem was he didn't write on very large-scale graphs. And when we tried to run it, we immediately got some memory errors. And then when we deep dive into the code, we saw that Spark has a relatively poor support for sparse matrix operation, or big sparse matrix operations. Then we had to implement this part ourselves, the matrix multiplication. So we have done that. It is working now. We have contributed it back to GitHub. You can find the MCL to use on Spark in the Spark extension packages. And this is our story with the MCL. So after this deep dive of the review of the algorithms, let's get back into context. So we were talking about our IPNet solution. We wanted to use the community detection algorithms. So now we have them. Now the real challenge is to choose between them. So on one hand, we have different results from different algorithms. On the other hand, we have no ground truth information on the real underlying communities that we are looking for. So we had to use a combination of a few methods. First, we manually prepared a few sets of tag data. This tagging was we take edges and just tag if the nodes on this edge should or should not be in the same cluster. We prepared some random sets. We prepared some biased sets towards the specific insights that we were looking for. And we used it to measure precision and recall on our clustering results. Next, we used some external data sources. So in the case of IPs, we could use the whois data. And we used it to check whether our intuition is correct, that IPs from the same whois or whois range should tend to be in the same cluster. Next, so usually community detection algorithm is just a step in a larger process. So in our case, we also used the measures we have on the whole IPNet process, meaning the transactions that are used from the communities that we created to choose the best algorithm that maximizes our overall results. And lastly, NMI, so that's short for normalized mutual information. It is a measure that is used to compare how similar two clustering results are. And it is usually used in the literature to compare between new algorithm results and the ground truth, but we didn't have ground truth. So we used it to compare different clustering results and to see whether one stands out from the other, for the worse or for the good. So this is some of the measures that help us decide the best algorithm. So I can tell you that we ended up using MCL for our first version of the solution. Then we switched to ravine in the second version of the solution because it gave comparative results but ran much faster. Now, the overall solution that I described, I think, of the IPNets is not very unique to the risk domain. So I'm sure every one of you from all the other domains might have similar usages to similar processes in your own domain. So this was our current work or former work. What are we looking on now? And what are we looking in the near future? So we are looking to extend our community detection algorithms to a Pregel-based algorithm. So Pregel is a graph algorithm approach invented by Google. And if you can implement your algorithm the Pregel way, you are assured that you can run it on multiple technologies. And better than that, you get freely all the optimizations that are meant for this kind of algorithms. Now, I'll just choose another one and tell you what we are looking in the near future. So most of the algorithms that we used are essentially unsupervised, and we are looking to make all the process much more supervised. So we're looking to find a supervised algorithm or semi-supervised algorithm. And I think I'll stop here if you have any questions. No. Okay, so thank you very much for listening.